knows the storm is coming fast, the day will soon be here, when those who are caught unprepared will be the first to fall, that much is clear.
Hello and welcome to Physical Attraction, the Teot Wauki specials, where we'll be examining the end of the world, one apocalypse at a time.
And survive while there's people crying, people dying everywhere around.
Hello and welcome to this episode, this Teot Wauki special of Physical Attraction. Today we're going to be talking about climate change versus the ozone layer and what we can do to actually fix this problem. So although it's heading towards an unprecedented number of episodes, I thought it would be worth spending a couple more episodes just talking about a few more aspects of climate change in addition to the ones we've already covered. Most of the scientific aspects I think were covered already, so this is predominantly going to be about solutions because there's so much political and scientific debate about the best thing to do, and I think it's worth discussing that given that it's an issue that affects us all, politically and personally. But I do think it's worth just reiterating before I get into this, the answer to the question, how do you know all this? Well, we know the Earth is getting warmer, this is indisputable. Measurements of the global mean temperature confirm it every year. You can see lots of lovely visualizations of this that NASA and NOAA and people like that put out. The sea level is rising, as you'd expect due to both ice caps melting and the oceans thermally expanding as water does when you heat it up. Actually, the thermal expansion is dominant at the moment because a lot of the ice that's melted has been in sea ice, which doesn't actually expand the volume of the ocean because, as you probably know, ice displaces less volume than water. In fact, much of the anthropogenic, that is human-generated heat due to additional CO2, has been absorbed by the oceans, perhaps as much as 90%. So we can see this evidence of the oceans getting more acidic and warmer by the unprecedented scale of the deaths of sensitive ecosystems like the coral reefs. Biologists see the effects of climate change in their work, as do people like oceanographers. 16 out of the 17 warmest years on record have occurred since 2001. The ice caps are gradually retreating, especially in the Arctic. Glaciers all over the world are also retreating. You can't deny the temperature change, and it's well outside of what you would normally expect, based on our paleoclimate records. There's a great XKCD comic for this, where they demonstrate the scale, in terms of time, of the natural variability. What makes anthropogenic climate change so obvious is the rate of change. It's not unusual for temperatures to change globally by a degree, but normally it takes place over thousands of years, not a few decades. In previous episodes, I described the physics basis for climate change, CO2 and other greenhouse gases, and the ways that they absorb and scatter light at different wavelengths. This is what causes the greenhouse effect. Shortwave radiation arrives from the sun. Some is reflected, and some is absorbed by the Earth, which then re-emits longwave radiation, because it's colder than the sun. More of the longwave radiation is scattered by CO2 and other greenhouse gases than the shortwave, so the atmosphere traps heat. It's not like a blanket, really, in the sense that there's no additional source of heat. The sun isn't getting any hotter or anything like that. It's just that it's failing to leave the Earth once it gets there. And we know from measurements at Mauna Loa and countless other measurements that carbon dioxide in the atmosphere has increased from 280 parts per million to more than 400 parts per million, and that it's increasing at an accelerating rate. And furthermore, we know from paleoclimate data that in the eras when we had higher concentrations of carbon dioxide in the atmosphere, the temperature was hotter, sometimes by a very large amount. Now, in climate change, we talk about two different responses. There's what you call the transient climate response and the equilibrium climate sensitivity. So the transient climate response is the kind of response that we'd expect to see by the end of the century, based on a doubling of carbon dioxide. And that's a guideline of the likely changes that we'll see by 2100 in our own lifetime. The equilibrium climate sensitivity says, okay, if you just switch the carbon content to, say, 400 parts per million, and then wait for 1,000 years, 2,000 years, what will the eventual temperature be? Currently, according to the IPCC, we're estimating that the transient climate response to a doubling of carbon dioxide is probably around 2.7 Kelvin, 2.7 degrees Celsius warming. And we estimate that the equilibrium climate sensitivity, that's a little bit harder to pin down, but it could be 3 degrees, could be 4 degrees, could be 5 degrees, anything in this range has been mooted and talked about. It would seem no coincidence that this step change in carbon dioxide in the atmosphere, in geological terms, it's increased from 280 parts per million to more than 400 parts per million over the course of a few decades. And it would seem no coincidence that this started just around the time that humans started pumping carbon into the atmosphere. The fossil fuels that we burn today took millions of years to form. This used to be one of the long, slow carbon cycle feedbacks that gradually exchanged carbon between the big sinks in the rocks, the deep ocean, and the biosphere, that is, living things. So if you go and see a graph of the Mauna Loa data, which you can find online, there's plenty of them, you'll notice that although the CO2 is generally rising, you actually see little cycles that it goes up and down slightly every year, with an amplitude of about 10 parts per million. So there's about 10 parts per million more CO2 in September than there is in, say, March or February. And the reason for this is just due to the presence of deciduous forests in the northern hemisphere and things like this. When it's winter, all of the creatures start to die, the leaves start to die, and this releases carbon into the atmosphere that's then sucked up again in spring. Now, in fact, with isotope analysis, you can tell where the carbon comes from. Plants and animals which later become fossil fuels, well, they preferentially absorb the slightly lighter isotope of carbon, C12, rather than the heavier one, C13. As the carbon content of the atmosphere is changing, that ratio is always changing. Now, this would either indicate that more living things are dying and dumping huge volumes of carbon into the atmosphere than ever before, or, far, far, far more likely, the fact that we're burning things that have died over millions of years is the equivalent of diluting the carbon-13 in the atmosphere with a whole bunch of dead biosphere stuff. People talk about the carbon cycle as having changed before, and it's true that carbon has always flowed through the system, but again, we're talking about different timescales here. This was on a timescale of thousands of years, or even tens of thousands of years. The rate of carbon dioxide in our atmosphere changing at the moment is closer to what you'd expect from supervolcanic eruptions. In fact, there's a classic example of previous timescales that comes from a much-studied period called the Paleocene-Eocene thermal maximum. So this is one of these times in our Earth's history when we've seen that the temperature was higher and the carbon dioxide was higher as well. And there we actually think that there was a temperature rise of around 5 to 8 degrees Celsius warmer than it is today, which is comparable with the absolute worst possible case of global warming. Although it is unlikely, current warming is about 1 degree Celsius. Back when that happened, back when we had this Paleocene-Eocene thermal maximum, the rate of carbon dioxide injection was only a few % of what it is today. It likely took place over hundreds if not thousands of years. People still debate what caused it. There was a recent paper that came out that said it was an unusual peak of volcanic activity that actually sort of dumped some carbon into the atmosphere from well below the Earth, in the mantle that normally doesn't surface. And so it was highly unusual in that sense. But the point is that, once again, even in this extreme circumstance that had a huge impact on the Earth's climate, it took hundreds of years to change carbon in the same way as we're doing at the moment. Similarly, when people tell you that the climate has always changed, that it's always warmed or cooled, for example, or that we're still coming out of an ice age, so the temperature change associated with an ice age, when you average it across the world, is 4 degrees Celsius. Like the temperature change due to global warming, it's amplified at the polar ice caps due to a number of feedback effects, including the ice albedo feedback that we talked about, and also the water vapour lapse rate feedback, which is very important, but I won't go into it now. This, perhaps the most rapid temperature changes we're used to seeing in the Earth system, would be the change from an ice age to a non-ice age, right? Because you have this huge ice albedo feedback where glaciation comes all the way down and then leaves again. Now, these very rapid temperature changes of 4 degrees Celsius, they're geologically rapid, which means they took place over perhaps 10,000 years. We're now talking about a 4 degrees Celsius rise over the course of a couple of centuries. Look at a graph of temperature on a 10,000 year timescale. You'll see that global temperatures rose by about half a degree and fell again during this time. But that rise and fall took thousands of years. So it's not just the fact that we're warming and that carbon is increasing, but the rate of change that makes us so sure that it's us. I heard a great lecture the other day where they said, yes, climate has always changed. But what we're doing now is more like the results of a meteor impact than a natural change. it is overwhelmingly clear that humans are driving much of the activity that takes place on Earth. This is true to the extent that geologists and Earth system scientists are calling this geological era not the Holocene or the Eocene, but the Anthropocene, the era driven by humans. Here's an example of the Anthropocene in action. If you consider vertebrates, that is, animals with a backbone, one of the ways of measuring them is by biomass. The biomass, the total weight of all these types of animal on Earth. Pretty much a third of the biomass of vertebrate animals is humans. Pretty much 2/3 is animals that we've domesticated. Less than 3% by mass is the animals with a backbone that would be here without our intervention. If you take into account both urbanised areas and agriculture, around 43% of the land on Earth is covered by humans, and we're influencing the rest. And how much of the rest is deserts and useless anyway? You can't expect burning millions of tons of fuel deposits to have zero effect. So I just want to reiterate all of this before I move on to a discussion of the politics, the economics, and everything else about climate change. Because there are questions that are worth asking, and there are questions that aren't worth asking anymore. We know this is happening. We know we're causing it. Anyone arguing these points is misinformed or lying to you for their own purposes. It amazes me how people can connect ludicrous conspiracy theory dots as proof and somehow blithely ignore this mountain of evidence. We have a range of estimates as to how bad it will be, that we're trying to improve and refine all the time. It's a very difficult task. The questions left to ask are, what will this do to us? What can we do to prevent or influence it? And should we do that? First, a detour into an illustrative example from history, the ozone layer. So one of the gases in our atmosphere is ozone. There's actually not all that much of it, so around 3 in 10 million parts of the atmosphere. Of all the molecules in the atmosphere, around 3 in 10 million are the ozone layer. And even the part that's called the ozone layer, only 1 in 100,000 molecules is actually made up of ozone. But it just goes to show how small amounts of the right molecule in the atmosphere can be very important for life. And if anyone ever says something like, oh, carbon dioxide can't have much of an impact, it's only 400 parts per million, that's hardly a big amount. Well, radiatively, it can be extremely important. And ozone is an example of that. It has an extremely important effect on Earth's radiative balance. So around 97 to 99% of the potentially harmful UV radiation, between 200 and 315 nanometers, is absorbed by the ozone layer. Sunburn is mostly caused by what isn't screened by the ozone layer. So the fact that if you lie out in the baking sun you'll get sunburn, that's mostly due to the 2 to 3% that escapes and gets through the ozone layer. This radiation is harmful to all living beings that we know of. Remember the unusually hot episode? Short wavelength radiation like short UV, X-rays and gamma. The photons have more energy, and so they can ionize matter more easily, which can damage cells and lead to cancer. So long-time listeners will remember that we had a Fermi and Drake episode, where we tried to talk about, why aren't there aliens talking to us, given how many habitable planets there potentially are. And one of the reasons people come up with is this rare Earth hypothesis, which is the idea that actually the requirements for life are far more stringent than we think they might be. And so it's possible to argue that perhaps you need an ozone layer and quite complicated chemistry in the stratosphere of your planet to prevent this damaging impact due to UV radiation that could sterilise and potentially kill all possible life on Earth. And this is why it was such a concern when, in the 1980s, we discovered that there was a rapidly growing hole in the ozone layer. Physicists and atmospheric chemists looked at the science, and they made their projections, and they were dire. So there was a more modern, sophisticated model that I'm going to refer to now. It worked out that if things continued by this rate, by 2065, the ozone hole would cover 2/3 of the globe. This model was an update on previous models that were slightly more optimistic. This confirmed that we were even closer to disaster than we thought, because the ozone layer collapsed far more rapidly in the middle of the Earth, in the mid-latitudes, than was expected. And this is due to a type of stratospheric cloud formation that basically took these ozone-destroying molecules high up into the clouds and the stratosphere and allowed them to destroy ozone more effectively. But I won't go into it in too much detail. So in this disastrous future, in 2065, if the ozone hole had continued growing unabated, going outside in a mid-latitude city like Washington DC would give you sunburn after 5 minutes. Not that you'd need to worry about sunburn, because the effects on plants, animals, and even the little microbes that fertilise the soil that turn out to be quite vulnerable, it would be devastating. Exactly how bad it would be if we were exposed to the full force of the sun's rays is unclear. But lots of people have projected that it would result in the deaths of pretty much all living beings on the surface. Like we discussed in relation to gamma-ray bursts and supernovae in the Teotwalki episode, It Came From Outer Space, stuff that lives under the ocean would probably be okay, because the water shields it from most of the radiation. That's why, although this scenario is devastating for life on the surface, it doesn't kill all life on Earth. And as we'll discuss, the ozone layer naturally replenishes on the timescale of a few years or decades. It's really only the fact that we kept pumping in chemicals that destroyed it that made the ozone hole sustain itself. So in this scenario, where we hadn't realised that there was an ozone hole, or that we just didn't care, I guess the ozone hole would have taken over the whole Earth, and humans perhaps would have become more or less extinct, or at any rate not at all industrialised, sheltering below big sunshades by 2100 or so, and then, since we'd stopped producing the chemicals that destroy the ozone layer, the ozone hole would heal itself, and the few surviving humans would have the chance to ruin the planet all over again. But that is an alternative history, and one that we thankfully managed to avoid. Scientists quickly realised that this was happening, that it was in fact potentially a huge problem, and we eventually determined the chemical reactions in the stratosphere that were causing it. Specifically, we were emitting chemicals into the atmosphere that catalyse the reactions that convert ozone, O3, into other types of oxygen. A chemical that catalyses a reaction essentially just makes it easier for that reaction to happen. The main chemical that we were doing was nitrogen oxide that was damaging the ozone layer, but the ones that caused the most damage were the chlorofluorocarbon compounds. These contained both fluorine and chlorine, which are at opposite ends of the periodic table, and therefore they bond together very strongly. This stability as a molecule made them useful for refrigerants and in other industrial applications, but it's also what allowed them to rise into the stratosphere without dissolving or decaying in any way. And then they got smashed up by the same UV rays that the ozone layer protects us from. The problem was that each molecule of CFC caused a chain reaction that could destroy 100,000 ozone molecules. So even in small quantities, it was causing a huge knock-on effect for the ozone layer. Well, you can do a little bit of rough calculations and say to yourself, well, if the atmosphere is 0.3 parts per million of ozone, and each CFC molecule can destroy 100,000 ozone molecules, to destroy them all, I guess you'd only need, 0.003 parts per billion? So 3 parts in a trillion or something of the atmosphere? Yeah, 3 parts in a trillion for the atmosphere of CFCs would be enough to completely destroy the ozone layer. So what happened was the world leaders got together, and they actually executed one of the better examples of global governance that we've ever seen. They enacted something called the Montreal Protocol. Only 14 years elapsed between the discovery of CFCs in the atmosphere, the realisation that they were contributing to the damage of the ozone layer, and then we had a treaty that effectively banned CFCs from being produced. Every nation in the world signed onto it in 1987. They all agreed to stop producing CFCs and replace them with alternative substances, and to regulate emissions of other substances that destroyed the ozone layer. And since then, countries have stuck to their targets. They've cut down on producing CFCs, and almost all of them have completely phased them out in favour of alternatives. As a result of our wise governance, nature is smiling on us. The newest observations show that although CFCs can hang around in the atmosphere for decades, their impact is already starting to diminish, and the hole in the ozone layer is starting to shrink. So this really is a pretty amazing scientific, environmental and governmental success story. The scientists noticed a problem. The governments acted. People complied with the regulations, and it worked. It represented evidence that we can act in a precautionary way, changing our behaviour now to protect ourselves from future potential for danger, rather than fixing a problem after it's already happened, which is almost always far more expensive. Scientists, policymakers and governments could coordinate on a big scientific project like this. The problem is getting substantially better. 98% of the ozone-depleting substances have been completely phased out. So obviously, climate change advocates look to Montreal and the story of the ozone layer to see if there's anything they can learn in the efforts to cut down on carbon emissions. And there are some obvious parallels. I mean, pollutants are being released by industry that had unforeseen impacts on the atmosphere. It put lives and the environment at risk, and the industry had to be regulated. The Montreal Treaty banning CFCs was signed in 1987, but as late as then, there were still people paid by the CFC industry arguing that the science was too uncertain to justify any action on CFCs. Does that sound familiar? But of course, the challenge of climate change is in many ways so much greater. There was a small number of industries using CFCs. Basically, it boiled down to two big companies that used them. Alternatives, hydrofluorocarbons, were available that weren't all that difficult to switch to for most industrial applications. Both of these meant that the industrial resistance to CFCs being banned, well, it existed, but it turned out to be possible to overwhelm it. It's actually the case that getting Montreal passed wasn't as simple as I made out above, because various governments, including the EU, were hesitant to sign on at first, until the weight of evidence became damning and due to public pressure. And that's also another reason that the CFC fight was easier. It's in terms of the science that we're actually communicating. So there's a great quote from Sheldon Ungar about communicating the problem with the ozone layer to the public, and specifically how easy it was to talk to them about the ozone shield and the ozone hole. He said, quote, "The idea of rays penetrating a damaged shield meshes nicely with abiding and resonant cultural motifs, including Hollywood affinities. These range from the shields on the Starship Enterprise to Star Wars. It is these pre-scientific bridging metaphors built around the penetration of a deteriorating shield that render the ozone problem relatively simple. That the ozone threat can be linked with Darth Vader means that it is encompassed in common sense understandings that are deeply ingrained and widely shared. People can believe in a shield, but maybe it's a little bit more difficult to think of gases that you release into the sky that act as a blanket. I've talked to several people about climate change who say, surely if we're releasing gases into the atmosphere, it blocks out the sun. To explain why that's not true, you need to talk about the radiative nature of molecules, and how it depends on frequency, which you don't learn about until late in your degree. There are all kinds of uncertainties and easily constructed denialist arguments that might convince people who don't understand the science, or who don't want to understand the science. Things like the climate has always changed, arguments driven by solar cycles, disputing the measurements, that kind of thing. The hole in the ozone layer, on the other hand, was so alarming, so rapid, and so unnatural, that it was pretty clear to most people that something bad was going on. It was easy to visualise, and because most people don't have much experience with the ozone layer, they're kind of more willing to take your word for it. That last remark might sound silly, but it's not really. A US senator once brought a snowball into the floor of the Senate to disprove global warming. Look, there's still snow. Saying that the world is getting warmer opens you up to all kinds of disputes between weather and climate. Some people will say weather is just weather, it's not climate change. It was pretty cold today, this winter, where I live. How can the world be warming? It's much harder to communicate things like a global average temperature that doesn't always reflect on people's lived experience. And then there's the facts and figures that we actually communicate to people. If you're telling people by mid-century, or by 2100, the ozone layer will be totally gone, everyone will get skin cancer, and it could kill all life on the surface of the Earth, people are going to respond to that. People are very concerned about things like skin cancer. They see this as a direct negative impact on themselves. Compare that to the climate change message you have to communicate. By the end of the century, the world could be 3 to 4 degrees Celsius warmer than it is today. People think about 3 to 4 degrees Celsius as a small temperature difference, maybe the difference between wearing an extra coat or risking it outside. Compared to looming death or skin cancer, it just doesn't have the same dramatic flair. And the idea that this takes place over decades, even centuries, leads to a general attitude of, why should I care? I'll be dead before this is important. But of course, when you know that 3 to 4 degrees Celsius in global average temperature is the difference between things being relatively okay and an ice age, maybe you start to think. But of course, we're all skirting around the major issue here. There is a big reason why there was no major public lobby, except for the paid attempts by the CFC industry, to deny the hole in the ozone layer, cast doubts on the science, or make it seem like a less important issue. There is a big reason why people are far more willing to believe the science on the ozone layer and come up with excuses for the science on climate change. There is a big reason why people are more willing to wave off the idea that this will be decades away, it won't affect me, it'll be a small problem. There is a big reason why the Montreal Protocol was a huge success, and the Kyoto Protocol, an equivalent attempt for greenhouse gases, was broadly speaking a failure. If all it took to stop global warming was to stop emitting some fairly obscure chemical like CFCs, we'd all be fine with it. In fact, when the ozone hole started, people started to stop using aerosol spray cans which contained CFCs voluntarily because they thought, I can help to the problem this way. Even if you had to stop using spray cans completely, people would come around, it would be easy to legislate. Instead, it seems by a lot of analyses that we need to completely remake our way of life. We are addicted to fossil fuels. The wealth of the modern world is founded on fossil fuels. There is no coincidence that the Industrial Revolution began as soon as we started widespread use of fossil fuels, and that the Earth's population started to shoot up to the ridiculous values that it is now. Well, not ridiculous, we talked about that in the Malthus episode, but the world's population exponential growth really kicked off when we started harnessing the energy of fossil fuels. With CFCs, we had good alternatives that we could switch to. In the case of CO2 emissions, much as I love renewable energy, it's far harder to switch to that, because the industry involved is thousands of times bigger, huge amounts of human activity with loads of companies involved. It affects everyone. Unless you have some really cool setup going, the energy that you're using up to listen to me, and the energy that I'm using to type this and run my laptop, is from fossil fuels. CFCs don't really enter into it. The same economic forces that govern our personal responses to mitigation also govern the responses of companies and governments. You often hear people making exceptions for themselves, or at least internally thinking, if not saying aloud, what's the point of me making efforts to reduce my carbon emissions when China, or fossil fuel companies, or Bob down the road who owns an SUV isn't doing the same? There's what economists call the first mover cost. Let's say you're the first energy company to say, okay, climate change is a big deal, we're going to either switch entirely to renewables, including somehow getting all of the storage and transport working, or we'll bury all of the carbon dioxide that we produce underground. If you're the only people who do that, the additional costs for switching to a cleaner way of life may well kill your company dead. So unless it's regulated, it doesn't happen. I'm going to present you with two views. One of them is orthodox, and the other one is just a little bit radical. Let's go radical first. Why can't we do a Montreal for fossil fuels? We got around the problem of companies wanting to emit planet-destroying chemicals by just legally forcing them to switch. There are only two major companies that produce CFCs, so once you force both of them into it, there was no first mover cost anymore, because we made them move at the same time. What if you made it a legal requirement for fossil fuel companies to bury an equivalent amount of carbon dioxide to the carbon that they extract from the ground? And in actual fact, this was done in a recent natural gas extraction in Australia, where they said a condition for you extracting and burning this gas is to bury an equivalent amount of CO2 in the ground. In some ways, you could argue about the fairness of all this. After all, we all drive that demand for energy, for oil, for coal, for natural gas. There's a simple answer to this. The free market economic system has a major flaw. It does not account for anything else aside from profit. So if you care about anything else aside from profit, that's where things like legislation and corporate responsibility come in. The job of legislation, the job of corporate responsibility, is to try and make the companies take other things like morality into account. Many companies find it profitable to treat their workers terribly. If they could force us to work 15-hour days with no sick leave or no benefits, or you're fired, and no weekends, the profit motive may well tell them to do that. We've decided that we don't want that, at least not in our backyard, so that the whole system is built on immense human suffering somewhere. And so we regulate the companies. The cost of doing business for that company goes up, because ethics is expensive. They now have to take care of their workers, which costs more. The price of whatever the company is producing similarly goes up, of course. This is the price that we pay for living in only partial servitude to the system. A similar thing could be done with carbon dioxide, controlling carbon at the pipeline rather than the exhaust pipe of our individual cars, as Professor Miles Allen, whose idea I'm nicking here, says. So if you're saying that it's unfair because we drive the demand, we would also pay the price because energy from fossil fuels would be more expensive. so driving your car. This would have a knock-on impact on demand, of course, and maybe we'd find that mitigating wasn't so difficult after all. But more than that, forcing the companies that extract fossil fuel to extract and burn the same amount of carbon would give them enormous economic incentive to bury the carbon. We talked about an astonishing thing in the peak oil episode. The ingenuity of these companies is amazing. They have this profit motive to find better solutions. That's why we keep burning more fossil fuels, and proven reserves keep going up, not down. We keep getting extraordinarily good at digging this stuff out of the ground. If similar financial incentives were devoted to carbon capture and storage, wouldn't that be much better than trying to do it with comparatively shoestring university budgets? Or startups that try to do it, like Climeworks in Switzerland? If they wanted to, with all these billions of dollars and scientists they have access to, there's no question that the fossil fuel company could come up with some better solutions than we have at the moment. So yes, this solution would solve all of our problems in one fell swoop. But that swoop is incredibly difficult. It would cost the fossil fuel companies billions of dollars, and it's thousands upon thousands of times cheaper for them to just buy a politician who would block this kind of policy from ever being enacted. If you think I'm being cynical, please understand that in the US, every election cycle, the fossil fuel industry spends $20 to $25 million on direct contributions to political campaigns. They're not doing that because they like politicians. It costs around $1.5 million to run a campaign and win a Senate seat in the United States. Politics there, in the world's leading democracy, apparently, is big business. So if it costs the fossil fuel companies billions, or even trillions, to sequester the CO2 that they're producing through their actions, it's always going to be far cheaper for them just to buy up the relative politicians and block the law. And of course, it's not just a US problem. You would need international agreement to do this and a very robust global governance framework, which we don't have at the moment. And you can see the problems that begin as soon as you start anything like this. I mean, the Paris Agreement worked, at least until Trump. The Paris Agreement was reasonably successful because there are these non-obligatory contributions. Everyone agrees to their own targets, which they set, and, they're not binding. They're not legally binding in any way. If your government is funded mostly by revenues from oil, coal, and natural gas, the fact that you can't legally extract these substances anymore without paying a carbon penalty makes them less valuable, because you stand to gain less profit than you do otherwise. Do you think Saudi Arabia or other companies and countries with lots of natural gas, coal, oil resources will enjoy that? How about Scotland? There will be winners and losers. Energy companies with lots of renewables will probably be able to supply cheaper energy, especially at first because the solutions for sequestering CO2 will start off more expensive. Although I should point out that actually they do have these methods of pumping CO2 into the ground that have been developed by the fossil fuel industry. That's where a lot of this technology comes from, and they do it in the sort of hydraulic fracking and so on to force more oil, coal and natural gas out, so they can do it for storage as well if they want to. From my perspective, given that fossil fuels will run out anyway, and eventually we need sustainable energy, so much the better. I mean, these companies aren't going to be around in 100 years or 200 years if their entire business model is based on extracting something that's going to run out. But if you're Shell, you won't see it that way. People will lose their jobs, and some companies may well go bankrupt. The planet would be saved. If it's a choice between the planet and the free market, I choose the first one, but unfortunately this is not a widespread viewpoint. So now for the non-radical perspective that I was going to give you, aside from the global government regulates all of the fossil fuel company viewpoint. Fossil fuels enter into our lives in so many ways. The electricity we use, yes, but also the coal on the fire, the petrol in our cars, taking flights. Stopping climate change, however we do it, will require huge, radical changes to the way that we live. I mean, just look at the industries that depend on fossil fuels and have this incentive not to reduce their consumption. We're talking about the energy industry, the fossil fuel industry, that supplies 80 to 90% of our power in the world. It's worth hundreds of billions of dollars, if not trillions of dollars every year. There are perhaps 3 trillion tons of oil reserves in the world. That's a bit optimistic, but we find new ways to extract all the time, as we learnt in the peak oil episode. At today's prices, that's $150 trillion of oil alone. Fossil fuels still supply the overwhelming majority of our energy, although renewables are growing fast. So the incentive for people to carry on using them is huge, which is why it's so much easier to downplay the problem, bury your head in the sand, cast aspersions about the science, and when all else fails, change the subject. It's always going to be cheaper for the fossil fuel companies to greenwash, do some good PR campaigns, bribe the appropriate politicians while sucking up whatever meagre social and economic damages we can levy against them with our do-goodery when we too still depend on these fossil fuels. And it's always going to be far more difficult for governments and environmentalists to regulate them. So yes, we can learn from Montreal about governance, about public awareness, and about how science can interact successfully with policy. But unfortunately, aspects of the problem make it harder to communicate and make the dangers harder to appreciate. And fossil fuels are far more ingrained into the modern world and our modern lives than CFCs ever were. Surprising no one, we're going to come back to this topic in the next episode. There I'll talk about the attempts that we have made to combat carbon emissions and greenhouse gases. I'll talk about the philosophical and personal aspects of climate change. I'll talk about the politics and the economics, and I'll talk about what we can do, what we should be pressuring our legislators to do, aside from, obviously, the rather radical scheme that was laid out a few sentences ago. And I'll talk about the changes that we can see in the world that will make the most impact over the coming decades. These are obviously all huge questions which thousands of people are researching, and I'll only begin to scratch the surface of them, but hopefully it will be somewhat useful. This is a dialogue between you and me and everyone on the planet. These existential risks that I've been talking about, not just in this episode, but in the last 10, 12, 15, however many we've done now, they are things we have to decide and agree on how to tackle together, because as Montreal shows, when we all act together we can get things done. But when there's thousands of people pulling in slightly different directions, we can't get anything done. That's just the way that it is. So, in that spirit, if you have any questions, comments, concerns, things you want me to talk about, things you want me to talk less about, go to www.physicspodcast.com. You can leave reviews there. You can follow us on Twitter @PhysicsPod. Tell your friends about the show. And, if your friends don't listen to podcasts habitually, which I know is the case, I've found in the podcast listening world, people either don't listen to them at all or they listen to dozens of them. And so some people have their own podcasting infrastructure set up where they listen to them habitually. For me, it's Apple Podcasts, I'm afraid. And that is what I'm still using, even though it's not the best app in the world. But anyway. They have their own infrastructure set up that they can easily add another pod onto the pile, but some people don't even know what they are, and they don't know how to listen. So if you're thinking someone might enjoy this show, but they don't listen already, well, you can tell them that you can find it on YouTube as Physical Attraction, and you can find it on Spotify as well, which I know a lot of people use, also just by searching for Physical Attraction in the podcast setup. So hopefully that will make things easier for more people to listen. Aside from that, on the website you'll find a donate button where you can give us some money if you think what we're doing is worthwhile. And you can also subscribe to us on Patreon or pay for an old back episode. For just $3 you'll get an episode of your choice from our back catalogue of bonus episodes. What else can you do? Yeah, just tell people about the show and tell people to consider existential risks in their day-to-day lives more and more. We'll be back next week with some climate change mitigation and some climate change controversies. Until then, be kind to each other.
You better make some preparations, there's no time for hesitations. Compile a list of tips.
Our theme music is Get Ready for the Apocalypse by Astrometrics.